Okay, folks, in this video, we're going to build upon some of what we knew from the one-way independent groups ANOVA, and now we're going to dig in and talk about the repeated measures ANOVA. So let's get started. So what are the real benefits of doing a repeated measures design? And there are really three things that I think come to mind. The first is sensitivity. The reason for that is when we perform a test and use the same person as their own control, we have much greater sensitivity in how changing the same person with different conditions causes that person to change. And so if a person has a dependent variable and that dependent variable changes, you'll see it in real time, and it could be directly attributed to the specific condition that the person received for the independent variable. The other thing is that by having a person serve as their own control, we don't have to worry about variance between groups. So it's not that these people are different than these people, because it's the same person who is just experiencing more than one condition. And so unsystematic variance completely eliminates the between group effects that we typically see in one-way independent groups ANOVAs. And thirdly is that the data is typically more sensitive to experimental effects. Okay, so if we have somebody sit for 40 minutes and then we have somebody exercise for 40 minutes, you will be able to observably see the difference of how a dependent variable did not change in a seated condition and how it did change in an exercise condition. So I hope that is helpful. The other thing that's important to understand is that in addition to these issues with sensitivity and reducing the unsystematic or error variance, is that when you have a person serve as their own control, you actually need less participants to do the study. You don't have to worry about the between group differences. And so this whole other group of people that you typically would need in an independent groups ANOVA, you just completely wipe that out because you have a similar group of people that's being tested over multiple time points or multiple conditions. And so because you don't have that extra variability, you need less people to successfully conduct your experiment and to reach statistical power. Okay, let's get into the theory of a one-way repeated measures ANOVA. So we still have to calculate the sum of squares total for the total variability, but remember, we do not have between group variance. So as you see on the left side of the slide, SSB is completely eliminated and gone. Instead, we're going to put all of our variance into the sum of squares within bucket here. And we're going to break it up into two components. One is going to be the sum of squares for the model, which represents the conditions and the effect of the experiment. And then the SSR is the sum of squares for the residuals, which represents still the error and the variability and the unsystematic variance. At the end of the day, it still comes down to explained over unexplained or systematic over unsystematic error. It's just how we're partitioning that variance in this particular case. But what are the problems? What are sort of the drawbacks of doing a repeated measures design? The problem is that you have the same participants in all conditions, right? You lose something by not having people who are not tied to each other. There could be a number of reasons why a person's dependent variable changes over time, not the least of which is the intervention. We also have the problem that scores across conditions from condition 1, condition 2, or condition 3, that they tend to correlate with each other because it's the same person, right? So the variable tends to move in a direction that is similar because it's tied to the person. Whereas we wouldn't necessarily have to worry about that correlation as much if we had truly independent samples and we had two groups where you definitively gave one group of people an intervention and one group of people the control. The last thing that we have to think about then is violations to the assumptions of independence. We have to check for the assumption of what's known as sphericity, which is similar to the Levine's test of equality of group variances for repeated measures designs. And we need to adjust for the degrees of freedom and correlations being similar. So we have a lot of other sort of needs when we're doing a one-way repeated measures ANOVA that we need to check for, but let's get into some of the basic assumptions. So what are the specific conditions that need to be met in order for the data to show what it intends to show? Well, the first is that the independent variable, which in this case is repeated measures in origin, must be nominal in nature, and the subjects, the people that represent our sample, must be tested repeatedly. The second is that our dependent variable of interest should be measured at least on an interval or ratio level of measurement. The third is that we have a dependent variable that is normally distributed. Okay, so condition 1, condition 2, and condition 3 should all be normally distributed. The fourth is that the variance or homogeneity of the variance assumption needs to be checked. And so the variance of different groups for the dependent variable need to be not statistically different, okay, which assumes that because these are the same people, the variance of condition 1 is similar to the variance of condition 2, and that is similar to the variance of condition 3. We also assume that the subjects that are recruited and enrolled in our study are randomly selected from the population. So I talked a little bit about this homogeneity of the variance assumption. And in independent groups, one-way ANOVA, recall that we use something called Levene's test for equality of group variance. But in a repeated measures ANOVA, we use something that's known as sphericity. And so what sphericity means is that the correlation between treatment conditions will be similar or not statistically tied or different from one another. Sphericity also assumes that the variance in the different conditions are equal, and it's measured using something that's known as Mauchly's test of sphericity. Similar to Levene's test of equality of group variances in one-way independent groups ANOVAs, we still want the p-value to be larger than 0.05, which indicates that there is not a statistically significant difference in the variance of condition 1, condition 2, and condition 3. So Mauchly's test of sphericity is to the repeated measures ANOVA, as the Levene's test for equality of group variance is to the one-way independent groups ANOVA. So what are some of the tools that we can use to estimate sphericity with Mauchly's test of sphericity? Well, when we run Mauchly's test of sphericity with our statistical analysis software, we're generally going to get a couple of estimates. We're going to get a greenhouse geyser estimate, we're going to get a lower bound estimate, and we're going to get a Hunfeld estimate. We're also going to get a sphericity assumed estimate. And it's important that if we have a p-value that is larger than 0.05, indicating that there is no statistically significant difference between the variances of our dependent variable across conditions, well, then we would use the sphericity assumed line in how we read and interpret the data that was analyzed and collected from our data set. If we violate the basic assumption of sphericity, however, meaning that we have an unequal distribution of variance in one condition versus another, our first go-to would be to read the greenhouse geyser estimate in order to do that. And so part of what our estimates of sphericity do is they're calculated by multiplying the degrees of freedom by these estimates to correct for sphericity. Okay? So what happens then if we conduct our analysis and we find a significant one-way repeated measures ANOVA? Meaning that the F critical value and the F observed value are different, meaning the F observed value exceeds the F critical value. Tells us that there's a statistically significant difference somewhere between the conditions or time points, but it doesn't tell us where, which is why we run post hocs. And so when we have a significant one-way repeated measures ANOVA, we'll run our post hocs with the same tools we used in the last lecture video on one-way independent groups ANOVAs, and we determine where those mean differences exist. So the thing that we need to think about, however, is based off of the number of groups or levels in our independent variable, we have to correct for the alpha rate in order to protect the family-wise error. And so the way you do it is by using the Bonferroni correction procedure by taking our alpha level, usually 0.05 in most cases, and dividing it by the number of tests, and that corrects the alpha level appropriately for the post hoc. So I hope this video was helpful. In the next video, we'll build upon our knowledge of one-way independent groups ANOVAs and one-way repeated measures ANOVAs and really start digging into post hocs. I'll see you there.